Alright, we're going to talk about Hess's Law. Sorry, I didn't write a title on here and just realized that. So this is Hess's Law. And what it allows us to do is calculate heats of reaction when it can't directly be measured in a calorimeter because it's part of several reactions or something like that. The rules of this is if you have to reverse a reaction, the sign of the delta H is also reversed. If you end up having to multiply a reaction, say your target has a coefficient of 2 and what you're working with only has a 1, then you multiply everything by 2, including the delta H. So we're going to work a sample problem. Let me get a decent color here. Alright. So here is our problem that we want to do. We want to find out, we got 2 carbons plus a hydrogen making C2H2. We want to find out what the overall delta H, how much energy is involved in this reaction. So we look at our, we go one reaction at a time, do one step at a time. We see here that we have C2H2, but it is on the reactant side here, but it's on the product side here. So what we have to do to this problem is we got to flip it. So now you see I flipped the first equation, and I also changed the sign of my delta H. So now we're going to go to the next problem. We see that we have 1 carbon here, but we need 2 carbons. They're both on the reactant side, but you don't have enough of them. So the next thing you have to do is you have to multiply that by 2, and you multiply everything by 2 in order to have your 2 carbons. So here we go. We have 2 carbons, 2 oxygens, 2 carbon monoxides, and I doubled that delta H. Now looking down here, we have our H2, and we have 1 of them, and that's where we want it. The oxygens we're going to cancel out, and we have the waters. So what's going to happen here is everything that's the same on both sides, just like in math, we cancel out. We have a water there and a water there. I have 2.5 or 5 halves oxygen on the reactant side. I have 5 halves oxygen on the product side. So we cancel those out, and what we're left with is our 2 carbons plus our hydrogen going to our C2H2, which is our ethene, and the total energy required for that, this is going to be required because this is positive, that means it's endothermic, is 226 kilojoules. So in order for this reaction to occur, you have to take it through the process and put in 226 kilojoules. Here is a challenge problem for you. This one is a little more involved. You do some flipping. You have to look, and sometimes you flip in order to be able to cancel out and everything else. But I'm going ahead and giving you the answer. Your answer is 11 kilojoules. See if you can do this before class, and we will go over this, and you'll have some practice problems and everything in class. Have a good weekend. Bye.